Clarity.
I think it's within the last few seconds for these, if I remember rightly, for the very big black holes. And then you feel it, and then it's tidal forces, but you wouldn't have time to react, really. You just go, that's a bit...
Right, but so you're not going to make an infinite number of quarks.
No, you won't make an infinite number of quarks.
Because time stops it.
Right.
I think
you
that's
actually
probably,
get to the end of time.
Having never thought about it, that's probably the answer.
Wow, that's a really... That's so
also... energy is conserved as well, so you couldn't make an infinite number of massive
Maybe
things,
it could evaporate the black hole.
So you'd be
It could turn the whole black hole into quarks.
Well,
because it's pulling energy out of the.
Well, no, the mass of the black hole will stay the same. So that process of hadronization.
No, I get that the mass will stay the same, but that mass energy budget is slowly getting converted into quarks. Because the quarks will keep making new quarks because you keep trying to rip them apart with your tidal forces.
So
you're saying that the quarks are a drain on the electric bill.
So you're saying that space-time would unwarp because the energy
will be completely converted
into matter.
And you have one giant quark. The quark catastrophe.
That's not what happens, isn't it? But it's
how do you know that's not what happens?
It's a brilliant question because we see black holes.
Oh, okay. Well,
so
that's the answer.
There you go.
Oh, yeah. No, okay, that's it. But I can't argue.
You cannot.
So they haven't. The geometry is not unfolded.
Then, so then you're left answering why it did not happen.
Right.
That's
and I think I suspect the answer is because of the finite time you have in there.
That's so cool.
So
all right.
But there's some weed for you now. You want some?
Yeah, please.
It's also important to say that we don't know what the singularity is.
Right.
So we really.
And we can't calculate with it or anything.
Yeah, because you can't get inside a black hole to see what it is.
Well, the theory.
Well, thank you for that. That was from an earlier Patreon question.
It's a great question.
I don't know. I don't know.
I'd never thought of it.
Yeah, that came from one of our listeners.
One of our people.
Yeah, one of our Patreon patrons. Which, by the way, you can be one for $5 a month as the entry, just to let you know.
It deserves more than it deserves the money back for that question. It's a great question. Refund.
Stump the expert.
You get a month free, buddy. That question was so great. That's funny.
Yeah.
Okay. So Raul starts us off. Raul. And he says, hello, Lord Nice, Dr. Tyson, Professor Cox. I'm Raul, a new Patreon member from a couple streets north of where you guys are right now on Central Park. I wanted to know if there was any thinking, discourse on whether dark matter and dark energy, affectionately dubbed as Fred and Wilma by Dr. Tyson, are emergent phenomena resulting from the curved manifold of space-time. In the case of dark energy, could it be that geometry of space allows for peaks and troughs for the accelerated expansion of space, and we just happen to be observing the expansion phase? Thanks for all that you continue to do for science.
I have to explain Fred and Wilma here before he begins.
Okay.
So I've had taken issue with the terms we have invoked to describe dark energy and dark matter, because it implies that it's energy and matter. And I said, what we know is that it's dark gravity. That is what it is. We don't know if it's matter. Maybe it is, probably it is, but we don't know.
Yeah.
And dark energy, is it energy? We don't know.
Yeah.
So I said we should just call them Fred and Wilma.
Yeah.
Okay? And that way there's no bias associated with the label.
Yeah, and that's how I was going to answer the question. Is in that there are different. So dark energy. So as you said, observationally, and we already mentioned Brian Schmitz, who was one of the people who discovered that the universe is accelerating. There is in Einstein's theory of general relativity a thing called the cosmological constant, which you can just put in, and it does that job. But whether that's what we're seeing is a good question, and we don't know the answer. So it could be that you're seeing some kind of quantum field, which we talked about earlier. So, for example, inflation, which is the idea that before the universe was hot and dense, so before what we call the hot Big Bang, then space was stretching extremely fast, driven by something which we call the Inflaton field, which is one of these quantum fields we talk about. And then that field changes and decays away. That's the end of inflation and the heating up of the universe, which we call the hot Big Bang. So it could be that dark energy is something like that. So it's some kind of quantum field that's doing it. That may mean that it changes and it could change over time. And indeed,
So it could
we
go
look for
away.
that. So it could go away. And I think that in the current data, which is associated with the early universe, there's a tension in between the things we measure, like the Hubble parameter and things like that, from the early universe, from the cosmic microwave background radiation, and the measurements from the later universe, which is from seeing supernova explosions and so on, seeing the expansion of the universe that way. And there are some sort of almost, probably not hand wave, but preliminary ideas that you could be seeing that something was present in the early universe that is not present now, or vice versa. So something's changed. So it is true that inflation would be an example, if it's correct, of one of those quantum fields which then changes and goes away. And that's associated with what we used to call the origin of the universe, right? Wow. So it could be that dark energy is something like that. And also, actually, to add to that mystery, there's the Higgs field. So the Higgs field is what's called a scalar field, which is technical jargon, but it's of the same type of thing that we think the Inflaton field is, and possibly the dark energy is. So but the Higgs field doesn't appear to cause the universe. Well, it does not cause the universe to accelerate in its expansion, or at least not in the way that we would expect. We'd expect it to blow the universe apart, and it doesn't. So there's something in there. Many of my colleagues think that associated with these things called scalar fields and the way they interact.
Is that something that's going to pop out of a future run of the Large Hadron Collider?
No, I don't think so. I think it's more theoretical advances that but precision measurements of the way the universe is expanding and has expanded, the expansion history of the universe. But these things are all encoded in there somewhere. So I think it's that. So the answer is to the question is we don't have a model. We don't have we have lots of models of what dark energy might be, but none of them are agreed upon or more convincing than the other. Right? We don't have enough measurement, I think, precision measurement. So it's a very good question. And the same with dark matter, we do have more evidence that it's some kind of particle. And some of that comes from, so I mentioned it, the cosmic microwave background. I should say what it is. It's the afterglow of the Big Bang. It's often described, the oldest light in the universe. So they're photons emitted about 380,000 years after the Big Bang, which we can detect. So it is a measurement. There's a satellite called Planck that made the highest resolution pictures of this that we have at the moment. And so in there, you can model the way that image looks. It's actually sound waves moving through the universe before 380,000 years after the Big Bang. So what you're seeing is sound waves in the plasma that was the early universe. And we can
seeing an imprint of those sound waves at
so
that time.
So you're seeing the imprint when the light got released, when the plasma went away. Yeah. Essentially what happens is...
So there was an actual bang?
No, I mean, that's what Fred Hoyle used the term, because he thought he was so stupid. It's not a bang.
Right.
As I described it, it's the end of inflation. So whatever. Exactly. We don't... But so these are sound waves. Wow. But we have a very good measurement. We have that photograph, which shows us there is the information about the sound waves. And that allows us to model what the plasma is and what's in it. And the dark matter is a very important component of modeling the way those sound waves behave. So it's not, it's often presented as something that people invented because they don't understand how galaxies rotate or interact or something like that.
That's a real thing.
But you can see it in many different ways. So it is true that the way that our theories of galaxy formation require it, there's a thing called the cosmic web that you've probably talked about before. But there's also independent measurements from the sound waves in the plasma of the young universe, and that requires them. And you can do, actually my postdoc actually did it for, it's one of the things that's in the show, not that I'm always plugging these tickets for the new show, but one of the things I do in the show is I mean my postdoc, Ross, is great, developed a real-time calculation tool of the way the sound waves work in the plasma. And what's cool about it is you can sit there with an iPad on stage and you can just go, I'll change the recipe. I'll make the dark matter go to like 15% rather than 25% or whatever it is. Play around with those things. And when you do that, the the data goes completely, it doesn't match the data. The prediction drifts completely from what we see in the data. So it's highly sensitive.
Wow.
It's a beautiful demonstration of how accurate astrophysics is now, how
very
accurate
cool.
cosmology is. So yeah, I would be very surprised if dark matter isn't some kind of particle
itself.
because there's multiple
Right.
different independent observations that suggest it is. Dark energy, we don't have precision,
Right.
the precision, I think, to discriminate between the models.
Cool, man.
And you thought I'd give long answers.
Well, it's a very good question. All right, I can see that we have to speed up. I'll speed up.
I'm good for long answers from either one of you. I don't
All right,
care.
keep
This
it
is
going.
Donita Bukait or Bushite, one or the other. And she says, "Hey, Neil, Brian, Chuck, Donita from Southern Utah. Help! I need visuals. How does the curvature of space-time cause tides? I've read explanations, but since I think in pictures, I need some visual support on this."
So imagine the Earth, and if you try to explain the tides in the ocean
Right.
by just having a static picture of the Earth and the Moon just standing
As is
still,
drawn in textbooks.
as is drawn in textbooks, then it's hard to figure out what's happening because, as Richard Feynman said in the Feynman lectures, if everything's just standing still, if the Moon and the Earth are just standing still, they'll just be pulled towards each other and squash
Like
into
two
each other.
magnets, like when you
Yeah.
set them down on a
Yes.
table and they whap come
Yeah.
together.
So, of course, the reason they don't do that is because they're in orbit around their common center of mass. So they're orbiting. And actually, you need to know that the Earth is actually orbiting around the center of mass of the Earth-Moon system, as is the Moon, in order to fully explain the tides. And so you get a good explanation. So there are centrifugal forces at work as well, because you're in this frame of reference that's spinning around and so on. So it's actually relatively easy to describe, but not as easy as it's presented on television usually.
Gotcha.
So,
And you got
but
into
it's
an
in-
argument with the producer on this.
Yeah, so I said I can't do it without talking about the fact that when there's a centrifugal forces. It's
Right.
basically because the centrifugal force exceeds the gravitational pull of the Moon on one side of the Earth,
Right.
and is smaller than it on the other one. It's that kind of effect, but it's beautifully described in the Feynman lectures, which are freely available online.
Is that right?
You can get
Online
them.
now?
I think they're
That's
free.
cool.
I spent real money on mine.
Well, the books
I have
you have to
hardcover.
get.
I have hardcover. I got them in the. When did I get them?
They're beautiful.
In 1981, I bought them.
Yeah.
Okay.
But it's in there. You can download. I think they're freely available now.
And there's
It's
three
worth
volumes,
looking.
right? So
Yeah.
classical mechanics, E&M, and then quantum.
Yeah, and it's in volume 1.
Very nice.
It's
Yeah.
really lovely explanation of it.
So there you have it, Donita. And also, you can check out the explainer that Neil did on tidal bulges. That might help you too, because it's really
I forgot
good.
about that.
It's correct.
You remember all of our explainers.
Why you think I do this job?
Okay. All
I
right.
get a free education. All right, here we go. This is Alyssa Feldhaus, sorry. Alyssa from Tucson, Arizona here. Question for Dr. Tyson and Dr. Cox. Do you think the concept of a particle will still be meaningful once we fully unify quantum mechanics and gravity, or will it vanish like the idea of a phlogiston did in chemistry?
No, it'll be meaningful. We've been talking about emergence a lot. So different levels of description. So yes, it may well be that there's a theory of nature that we have it, right? It's quantum field theory, that just quantum fields, and there may be a deeper level in terms of qubits or whatever those things are, Planck scale things. But there will always be a level of description that where particles are the right thing. I mean, think about an old-fashioned TV, a cathode ray tube, where you have a beam of electrons, and the beam of electrons goes through a magnetic field, and it jiggles the beam around, and you get the picture on the TV. There's never going to be a better description of that than a beam of electrons.
Right.
So maybe a deeper part of that question is, if we come to understand that everything is strings, then we don't need the language of particles. Or once again, is it just a convenience?
You will need the language of particles to explain things that are happening in this room, these energies and temperatures. Because
that's
there's
how it manifests.
Yeah, it's just pointless. You would
Okay.
why you wouldn't talk about these phenomena that only become important for your description of the world at energies that, trillions of a second after the Big Bang. or
Yeah.
something like
Okay.
that.
Okay.
I mean, just to say quarks, right? Quarks are not that you don't need those to describe nuclear physics. You want protons and neutrons.
Right.
Those are the things
Those are
that
the
you
things
need.
that, right.
Right.
Yeah.
And so the quarks are hidden inside. You don't feel that them. You don't perceive them. You know, that's why we didn't discover them until 1968, I think.
Yeah, yeah. Late. It was pretty late. You were on our way to the moon, and we don't yet know that quarks are real. Yeah.
That's wild.
Yeah.
That is wild.
All right.
We're stupid. Okay. This is David Villasmil, who
Is that
says,
the best you can do with these people's names?
hey, listen,
Chuck.
that's his name now.
Villasmil.
Yeah.
Villasmil.
Villasmil. Okay. Yeah.
That's his
You
name.
made him French.
That's what I'm saying. That's his name now, Villasmil. So this is anyway. He says, "Hello, Dr. Cox. I've been a fan forever.
All right.
Dr. Tyson and Dr. Tice, you guys are awesome. Anyway, how do particles know it's time to decay?
Love that question.
That's a great question.
Yeah.
Sorry about your name, David, because since you asked such a great question,
So what's the best way of describing that? Is time. So they have a lifetime, which is, as I said before, is to do with, can you decay into something lighter? So there might be a reason you can't, right? Because things are like electric charge, for example. Electric charge is conserved. So you can't take a positive charge thing and have it decay into a lighter, negatively charged thing, because you'd be inventing. You can't destroy and create electric charge. You have to do it in pairs. It's conserved. A very important example is the neutron and the proton. So the neutron is a bit heavier than the proton. So the neutron can change into a proton.
And does.
And does in about 10 minutes.
Yeah.
Oh, so,
I thought it was even quicker
it's
than
on
like
its
6
own.
minutes.
Is it or 8 minutes? I can't
Yeah,
remember.
it's like you can count it out and watch
and watch it happen.
Yeah,
so
yeah.
if it's sat on its own, it'll do that, and to conserve charge, there'll be a positive thing will go as well, and so basically it can do it. So, and the lifetime is really proportional to the difference in mass between the neutron and the proton, which is very tiny. So if it was really big, if it was much heavier, it'd decay quicker. So you've got there's the mass difference, and then there's the number of things you can decay into, the number of ways you can do it.
Yeah, but that's just a statistical average. The decay time. That's the half-life.
Yes, half-life.
Okay,
Yeah.
so we fill out the time with some of them are decaying sooner or longer. So it's not just as simple as you described, where how much difference is there in the energy of the mass of what it is and what it can be, because there's a variation in there. And I interpret that question as, how do you get that variation?
Oh well, that's quantum mechanics. So it's statistical.
Don't say that's an answer.
Well, no, but you're right. It's a very deep question.
Yeah.
It's like, and that bothered immensely the early founders of quantum mechanics. So people like Rutherford and those people who Niels Bohr and all those people, and Einstein, it bothered a lot. God does not play dice with the universe. That's essentially what you're saying. You're saying, why does God play dice, as Einstein put it? So the reason
He was late on the mortgage for the universe.
Yeah.
So he plays dice to get some extra cash on the side.
Papa got to make this money.
So I think it was
Papa got to make this money, baby. Come on.
Wait, but Brian, I realized just while you were speaking that you did answer her question precisely, because she said, because why does some take longer than others?
Yeah.
And the difference in how many options it has coming out the other side.
and the mass difference.
And the mass difference. So that'll say why one will decay in 5 minutes or 10 hours. You can get that.
Yeah.
Okay. Given that, what is going on at the instant that it decays?
It's another
Because
question.
does that give me insight into why some will decay sooner and some will decay later, so that it averages out to that half-life?
So what's going on? So you can, it's called the weak nuclear force that's changing these things. So that's part of the standard model. So what actually happens when a neutron turns into a proton? So a down quark turns into an up quark. So what happens is the down quark, you can think of it as emitting a particle, a force carrying particle comes up. It's a W minus, which then goes to an electron and a thing called an anti-electron neutrino, actually. But it goes, so the W minus goes off, and then you get a down quark, which is a charge plus 2/3.
Okay.
So you get a minus 1/3 quark going to a plus 2/3 quark, and then you get an electron that comes off. So all the charges are conserved. So you haven't invented electric charge.
Right.
And
So
also
the
when
sum of all the charges at the end is the same. as
we
the
got
sum
it.
of
And when we think of a neutron decaying to a proton, all that's the engine process going on. That's the gearing that's happening that you just described.
So it's the same kind of picture as why does an electron bounce off another electron? So we'd say, well, because they've got negative charge and negative charges repel. But the particle physics picture of that is that a photon is exchanged between the electrons. So in this case, it's not the electromagnetic force, it's called the weak nuclear force. Basically, the down quark is changing into an up quark with ultimately the emission of an electron and a neutrino, and the W minus is the particle.
And in the end, when that happens, is statistical. We got to deal with that. Are we hiding our awareness of objective reality by dusting it into the bin of probability?
No, it's not the same. That randomness is not the same as the randomness because we don't know everything. So in terms of a gas, let's say, there are things are jiggling around. We don't keep track. We spoke about it earlier. We don't keep track of the billions of molecules in the gas. So there's some statistics comes in because we're averaging over a load. The quantum mechanics is not like that, as far as we can tell. The statistical nature of it is inherently, it's built into the theory, it's built into nature. That bothered everybody.
So Einstein was just wrong.
Yes. Yeah.
Well, Einstein didn't like it. It is true that how to interpret that, then it's a whole other episode, right? So you've probably talked to people about the many worlds interpretation of quantum mechanics. No, that's all. That's this thing. That's all in this. How do you interpret those statistical predictions
without
the collapse of the wave function,
without invoking a statistical description?
Yeah, I mean, so it seems that it's a fundamental part of the theory.
My favorite part of particle decay?
What's that?
If you accelerate them,
right,
then they take longer to decay.
That makes sense.
Because Einstein's special theory of relativity.
That's
so badass.
Going closer to the speed of light, so time literally is slowing down.
And so it takes longer to decay.
Yeah.
That's a beautiful thing.
That's very cool, man.
Yeah.
Wow. All right.
Time for a few more.
All right, here we go. This is John. He says, hello, Lord Nice and Dr. Tyson, Dr. Cox. John from Arkansas here. You've both explained what a Planck length is and how we will likely never get more accurate measurements beyond this supposed limit. I am wondering if light can have a wavelength that small and if energy would be measurable, or could that be another infinity we need new physics to explain, much like the singularity in a black hole? P.S. Love the show, and Chuck, I figured I'd mention you first for a change. Anyway,
there is an answer to this.
I love this question.
Yeah,
I would not have been able to answer this question.
The answer is that so the smaller you make the wavelength of a photon, the higher the energy.
Yes.
So
there should be an energy associated with the wavelength that is a Planck length.
Yes. And you find out that that's that energy density makes a black hole. So I think
oh my effing God!
So if you think about it, the more you try to probe smaller, and then the black hole would. I think Len Suskind calls it the UV-IR connection. I think that's what he calls it. So the upshot is that if you try to put more and more energy into a smaller and smaller space to see smaller things, the size of the black hole you make increases. It grows.
That's wild.
So the more you try to see smaller things, the less you can see the small things. Right. Because the black hole gets
the universe
bigger.
is diabolical.
Yes.
Yeah. So it stops you. So you can't probe it.
So black holes are in the Cosmological Witness Protection Program.
Yeah.
You can't get in there.
You just can't, no matter what you do, you're not going to. That's amazing. What a great question, bro. That was awesome.
Okay,
All right.
and just remind us briefly about a Planck length. Just put that on the map here.
So you can construct units, fundamental units from things like, so from specifically the speed of light, the strength of gravity, and Planck's constant. So if you take those things and put them together, so you get meters out, you'll get the Planck length. So it's Planck who figured out that it would be good to make units of measurement out of things on which everyone would agree. If you think if you meet an alien, for example, then there's no point in talking about a meter, because what is it? It's the length of your arm or something like that.
Oh, no, it's 1/10 millionth the length of a quarter of the Earth from the North Pole to the equator through the Paris Observatory.
Oh, is that what it is?
Yes.
Right, okay.
That's why
Right.
the circumference of the Earth is 40 million meters. Which is, and make that kilometers. It's 40,000 kilometers.
Right, so
is the
it
circumference.
comes from-
That's why it's that even.
Yeah.
It's the French did that, but
So
you're
they're all
Brits, so you don't
arbitrary.
care what they did.
Yeah, so they're all arbitrary things that are to do
Yeah.
with our planet or our bodies or whatever it
Yeah,
is.
yeah.
But then you could say, well, but the speed of light, Planck's constant, and the strength of gravity, everyone would agree on.
Even aliens.
So
yes.
yeah, because you
Yeah.
can measure those. So whatever units you measure them in, you can put them together to make something that looks like a length. And
Gotcha.
that's the Planck length. And it happens to be very, very tiny relative to us.
Right.
Very cool.
So can there be a fabric of space-time that, in other words, if you were to quantize general relativity, you would have to, the Planck length would be fundamental to that. Is that not right?
Yeah. So we
Yeah.
think that's telling us something deep about the universe itself.
Okay.
So these are properties of the universe, these things.
Mm-hmm.
That's the
Right.
thing, not properties of planets or
Right.
people.
Right. Exactly. All right.
Very, very cool.
All
Okay.
right, time for two, maybe one more. All right. What do you got?
All right, This is Big Stu. And Big Stu says, hey, what it do? My name is Big Stu from Austin, Texas.
All right.
I've heard Dr. Cox talk about how information that falls into a black hole might not actually be lost. But what is that information exactly? Does Hawking radiation somehow contain the same atoms that went in? Or does the universe just eject some cosmic thumb drive full of data? I'm trying to wrap my head around this, man. Help me.
Cosmic thumb drive full of data, yes.
Yeah.
So the idea is that the Hawking radiation ends up, yes, the description that who was asked the question?
Stu.
That Stu said is basically right. So in more technical terms, you end up with this Hawking radiation. You'd have to collect it and do some operations on it with a quantum computer to kind of extract the information. So it's all, no one's ever going to do it. It's impossible to do in practice. But that's the idea. In a very fundamental sense, it's in there. In the same way that I suppose the information, if you were to, I suppose, ask the question, how is the information from this photograph I took with my phone encoded in the memory of the phone? It's quite complicated, actually, and it's got error correction in it and all sorts of things like that. And it's that idea, really, but at a quantum mechanical level. So,
Cool.
yeah. So it's not physically
Right.
the physical stuff, but it's the data.
Cool. Very cool.
Time for one more.
All right, this is Wayne Rasmussen, and Wayne says, hello, star nerds.
Nerds unite.
Yes.
Nerds of the world.
Does Newton's third law hold true in quantum mechanics? Wayne from Northridge, California.
To every action, there is an equal and opposite reaction. Yeah.
That was simple. Good enough for me.
I mean,
Yeah, I
so
can't
let
think
me
of any
broaden
reason why
that.
not.
Allow me to broaden it. So quantum physics and relativity has shown that the applicability of Newton's laws has limits. F is not always ma in that simple form. You need Einsteinian extensions on these constructs.
Yeah.
So even with his gravity equation, you have to modify it. And it was hard-earned to learn that Newton's laws fail. So does every action is an equal and opposite reaction have a point of failure where we need a deeper understanding or an updated understanding of how the universe works?
No. So for example, it's easier to explain the first law, everything continues in its state of rest, or uniform motion in a straight line, unless acted upon by a force. That is to do with the symmetries of space-time, right? So that is true in relativity as well. So if you if you're talking about special relativity, and it's one of the examples we teach actually in our first year undergraduate course, you can show that if something's traveling in a straight line in one frame of reference, it's traveling in a straight line in a different frame of reference under both Galilean transformations, which are the Newtonian picture, and Lorentz transformations, which are the special relativistic picture.
Both of them. Okay. Very good.
So you could actually phrase that as one of Einstein's postulates, because Einstein's two postulates from which special relativity emerges are the speed of light's a constant for all observers, and the laws of nature take the same form in all inertial frames of reference. Newton's law that says that something's going in a straight line, unless acted upon by a force, it'll still carry on going in a straight line, is one of those laws. I mean, if you think about the consequences, otherwise you'd be able to change between different points of view moving at the same speed relative to each other. And something that was going along in a straight line, according to one person, would be doing that. Would be in an orbit or something.
Mm-hmm. We're intact
built
there.
in. So they're a representation of the, ultimately of the, and there's a very deep question as to why is that the case? And I remember again Feynman, who we mentioned earlier, talking about it. Why is that the case? And he said it's because it's one of the fundamental properties of our universe. So we don't know why that's the case.
It just is.
That is the way our universe is built. It's to do with the posh way or whatever the fancy way of saying it is the symmetries of space-time. But it's just, that's one of the fundamental properties of our universe.
I'm going to end with something completely irrelevant.
Okay.
But he mentioned the Galilean transformation.
Yes.
There's a game played by the Seattle Seahawks.
Correct.
And I'm in email
with Pete Carroll.
With Pete Carroll, okay? So I'm on his radar, he's on my radar, and their quarterback did a lateral on the field that was being challenged by the opposing side.
I say illegal forward pass.
Illegal forward pass. He's already passed the line of scrimmage, and he's going to his running back, tosses it to the running back catches it, and they get a first down, and they would ultimately score. And he said to me, Neil, I think what we did was legit. What can you help me here? And I looked at it, and so I posted online that it was a legitimate Galilean transformation. So here's what's happening. He and his running back are running down the field. He is ahead of his running back. He pitches to his running back. He's ahead of his running back when he let go of the ball. He's ahead of the running back when the running back caught it.
Right.
Okay?
And he lets go of the ball before the line of scrimmage.
No, it's after the line of scrimmage.
No, that would be an illegal forward pass.
I'm getting, no.
No, he has to let go of the ball before the line of scrimmage.
No.
The receiver caught it after the line of scrimmage.
No.
That's the only way this can work.
No.
Okay,
Hear me out.
let me hear you.
Please.
Go ahead.
Please. They both are well past the line of scrimmage. Both of them. He's ahead of his receiver, pitches it backwards to him.
Oh, you mean they're running together?
Yes.
Oh, that's a different story. Go ahead.
Pitches it back to his running back.
Right.
Okay? The whole time he's in front of him.
That's correct.
But they're running so fast that from the reference frame of the gridiron, the ball actually went forward.
No, that makes sense.
Okay.
Yes.
So I said, this is a Galilean transformation. You cannot penalize football players for running
being fast.
Okay. Right. You can't do that.
Should have been two white players.
Stop. He's in race therapy. He's getting out of it. He's gotten much better, by the way.
Funny. That was funny.
It was two black players, by the
way. They're fast. What can we say? Okay, go ahead.
So it turns out that they let the call stay that it was a legitimate lateral. Even though, according to the field, it was a forward pass.
No, it would have looked like if you're running fast, that's what it would look like.
Yeah, and so that was a Galilean transformation where whatever else is happening, your reference frame is moving and everything is happening in that moving reference frame.
Very cool.
Galilean transformation.
Awesome.
Yep. Yeah.
Science.
You know how we did it on an explainer once. Have you ever been on the highway and then these cars racing each other around you?
Oh yeah, that was
It feels really dangerous.
Right.
But in fact, as far as they're concerned, you're just standing still.
Right.
And they're just darting around you.
Yeah.
And so they're in their own reference frame, and you're just blockage.
Yeah. So there's
we're all going 40 miles an hour in slow traffic, and they're going 70 miles an hour around us.
Right.
And it's less dangerous than it looks, is all I'm saying.
But don't do it, Peter. Okay? Follow the laws of the road.
Brian!
And buckle up.
Delight to have you visit
Always a
our
pleasure.
humble city, my humble office. Don't be such a stranger. But you're a busy guy, so we allow this.
Yeah.
Oh, okay.
And we'll look forward to your emergence tour. I assume it's another international booked tour.
Yeah, it comes to the US, and I think the tickets are on sale for the end of next year and the start of 27.
Damn, the boy's got his
man, he's
calendar.
already.
The New York date, the East Coast dates are not yet on sale actually, but they will be.
Okay.
Okay.
You gonna come back to the Beacon Theater, which is where I last saw you?
I think so.
No,
I
he's going to
think.
say, I'm coming to
We're
Yankee
moving up.
Stadium.
Yeah.
Giant
moving up.
stadium.